All right, so as Greg mentioned, I'm going to talk to you guys a little bit on how we initially approach creating a coarse-grain model. In particular, in this talk, I'm going to focus on stuff that we use to start with an all-atom system and build a coarse-grain model. In the case of HIV, as he talked about, more or less, it's not quite a bottom-up approach for that, and so I'm not really going to talk about that kind of a project, but more about how you start from the underlying atomistic information and you build a coarse-grain model. And within that paradigm, there are two issues that come to mind that we try to separate. One is, where do we place these sites in the molecule? What are the sort of optimal positions for these coarse-grain sites? So in this case, this is actin, and there's 12 sites. And where how many sites are there, should there be, and where should we place them? And we try to separate that from deriving the interaction potentials once we have these sites. So, and within the site placement aspect, I'll briefly mention, I'll mention two things, but briefly mention one approach called the shape-based coarse graining, which was developed by the Schulten group down at UIUC, and I'll just mention that as a counterexample to what we use in the group mainly, which is called essential dynamics coarse graining. And then within the interaction parameter development, I will discuss three aspects, although if I probably won't have time to get to some of them, but two of them we use in the group. One's called hetero-ENM. I'll talk about that. So hetero-elastic network model. And then the second is charge fitting. But before that, I'll mention what's either called inverse or iterative Boltzmann approach to deriving parameters between the interaction parameters between these coarse-grained sites. So to go back to what Greg mentioned a little bit, this is not when he was talking about the force matching aspect at the beginning of his talk, which is for a finer scale coarse-grain model. This is more ultra coarse-graining, mean a bunch of amino acids per coarse-grained bead. So you can't really tie it to that as nicely to the underlying statistical mechanics as you can for the sort of more fine scale, few atoms per coarse-grained site approach. So first, I'll talk about the site placement aspects. And by the way, interrupt me at any time and ask questions. It's fine. So as I said, I'll briefly mention shape-based coarse graining. And this is developed by the Schulten group down at UIUC, and it's actually implemented in VMD, which is very nice for anyone who just wants to use it. And the idea here is basically you take a static atomistic structure, and actually it doesn't need to be quite atomistic, but you take a static structure, one particular structure, and then you try to replicate the shape or the mass density of this structure using a fixed number of coarse-grained sites. And so then for the N-bar protein, if you take the N-bar protein, which Greg mentioned a little bit, and I'll mention a few times during this talk, and you try to place 40 coarse-grained sites on it using the VMD tool, this is what you get out. Okay? And the basic idea is that it replicates the shape quite nicely. And the underlying atomistic ribbon structure is shown slightly transparent here, and then the coarse-grained beads are in this cyan color beads. So that's just where they place them. And then once they place these sites, they actually assign the underlying atoms that by some sort of the closest atoms to this coarse-grained site get assigned to that coarse-grained site. And then you can think about how you might develop the parameters based on the underlying atoms, which we'll talk about in the second part of my talk. But what we tend to use is what's called essential dynamics coarse graining, or EDCG. And the idea behind this is that you, instead of just using the static structure and fitting a mass density, you actually try to place the sites in such a way that you can reproduce the main motions of a particular protein or a particular molecule or whatever you're looking at. So in this case right here, again, I have the N-bar protein, and I have depicted in sort of a porcupine plot the first principal component mode. What? I don't know what that means.
Sorry, 1 second.
Okay, some issue.
Yeah.
Yeah, sure.
So when you talk about motions,
Mm-hmm.
I mean, I assume your system is not equilibrated.
So
your knowledge about the system, I mean, like.
So for these systems, you can equilibrate. I mean, the N-bar protein, for example, that I was showing there is, 400 and something amino acids, and actually, in that case, it's also in a lipid membrane. And so you can make a good approach, a good attempt at equilibrating that atomistically. So then you have an atomistic trajectory, that was quick, of this motion, which you prove is equilibrated, or you try to show is equilibrated using standard MD tools. And then from the equilibrated data, you do some sort of, well, in this case, you'll do PCA, which is called principal component analysis, and in order to develop, to assign different modes of motion to the molecule. So, no, I mean it's sort of similar to normal mode analysis for like water or something like that, right? Water has particular normal modes, opening and whatever. So it's the same idea in some sense. It's a little bit different. I'll talk about each of these 3 points in more detail in the next few slides. But the idea is, if you do equilibrated structures, you actually can run this atomistic structure and equilibrate it. You can do what's called principal component analysis, which has been shown to be pretty good for describing the main motion of a protein. But if you only have a static structure and you still have the underlying atomistic force field, you can actually do a normal mode analysis and get the normal modes for the protein and try to fit using the normal mode analysis. But no matter what sort of motion decomposition you do, you then choose an essential subset of modes. Because you're coarse graining this thing, you're going from 3n minus 6, where n is number of atoms, number of modes, to 3n Cg minus 6 number of modes. So you're going to choose what we call an essential subset of modes. So whatever that might be, 5, 10, 100, 200, depending on your system. And then you try to place the coarse-grained sites in such a way to optimally reproduce those modes with the center of mass mapping to your coarse-grained sites. So, as I said, you can calculate these modes using either normal mode or principal component analysis. For the sake of this talk, I will only talk about principal component analysis. And what this is basically you calculate the covariance throughout your trajectory, the ensemble average of the covariance of the positions of the atoms. And all this basically tells you is, do these atoms fluctuate in a correlated fashion and anti-correlated? So this would be fluctuating about their average in a correlated fashion. This would be fluctuating in an anti-correlated fashion where the covariance is negative. And then this would be fluctuating in a non-correlated fashion where the covariance is essentially 0. Okay, so you calculate this matrix, this covariance. In this case, this is a matrix element, but the matrix from your atomistic trajectory, and then you diagonalize the covariant matrix to get the what are called the principal component modes. So this is very similar to a normal mode analysis, and you'll essentially get a bunch of eigenvalues and eigenvectors from this diagonalization, from which we actually then just select what we call, as again, the essential dynamics subspace or essential subspace. And all that is taking the highest frequency or slowest modes of motion for some given cutoff. So I might say I want to reproduce 95% of my motion. By that I mean I want to take the the modes that compose 95% of the overall motion based on the frequency of these modes. So in the case of the N-bar protein, I have the 3 principal component, the first 3, so that means the 3 slowest modes from the principal component analysis, depicted here by porcupine plots. And I mean, you can kind of see that in the first mode, you're bending in, and the membrane, would be here. So in the first mode of this protein would be, bending in towards towards the membrane, and then this one is sort of a rotation of each monomer, and this is another rotation of each monomer. But the basic idea is you select whatever essential subspace you want, and then you try to minimize the residual, which is defined as chi squared here. And all that is the difference between the sum of all of the atomic vectors in that mode at their positions versus mapping them and summing them to the center of mass of their coarse-grained site. So you can do this in two limits in essential dynamics coarse graining, that of sequence-based versus space-based coarse graining. And the idea here is very simple. If you have a 10 amino acid sequence here, then sequence-based only allows you to group these atoms in sequential segments. So in the case of, if I wanted to create 3 coarse-grained sites here, these red bars would depict the boundaries of these coarse-grained sites. And so I would have a coarse-grained site which is composed of amino acids 1 through 3, 4 through 7, and 8 through 10. So that's the idea of sequence-based. And it's very simple. Space-based, however, would allow you to group it however you want. So in this case, you could have, you could have 1, 10, and 5 grouped together, and 2, 7, and 9 grouped together, and so they don't have to be sequential. So what limit you choose depends on your system, potentially. But you can also think of this as a clustering-based problem. So if you again look at the residual, which is just, which you can decompose into a pairwise residual, just taking out each pair, and you look at it as a matrix, you can do this as a matrix clustering problem. And the sequence-based is in this simple case of just a 3 by 3 matrix, you can think of this as just looking at off-diagonal elements and clustering based on that matrix. Whereas the space-based is all elements of this, in this case, would be a residual matrix, and clustering based on that. So you just cluster the most correlated atoms initially in the space-based approach, but they could be on opposite sides of the protein, which, depending on what you want to do with your system or how you think about your system, that may or may not be valid. So these are the two limits, and obviously there's, in this case, it's a 3 by 3, so you either have sequence-based or space-based, but there's obviously somewhat of a continuum in there for longer sequences. Then ultimately, what do you get out of this? So I've run, in this case, sequence-based EDCG on the same molecule as I showed you for space-based. And again, you get something very similar to the shape-based coarse graining. You get these coarse-grained beads, which in general depict the shape of the molecule and are equally, or somewhat equally distributed throughout the protein. So let's compare and contrast these two methods. The shape-based coarse graining, as I said, places sites on a static structure. So all you need is one particular structure. And it just tries to fit the mass density, basically. EDCG tries to place coarse-grained sites to match all atom fluctuations. So it tries to optimally reproduce any motion that your protein undergoes. The downfall, or the pitfall of both methods is that they actually require a specific choice of the number of coarse-grained sites. So, there's been a couple papers published on how you might choose that, but really, as of it stands right now, it's somewhat intuition-based. You can look at things like the residual versus number of coarse-grained sites from EDCG, and you always get a power law dependence, basically. And so it's kind of unclear from this plot, or it's unclear completely to me, what would be the optimal choice of the number of coarse-grained sites here. So there's no sort of dip and peak and things like that. Yeah? Mm-hmm. So it does that does not matter. That's one idea. You might look at it and say, here there's dense parts here, here, and here, so I might think of 4 sites or something like that. But in any of these methods that I've mentioned, that it doesn't matter if they have the same mass or not.
Residual, it's basically trying, as you say, it's trying to group things,
Mm-hmm.
but it's looking only at a single resolution. Is that right? Like I guess you could also imagine a residual in terms, that explicitly tries to do what you have up there. It said that I vary my plates around and I compare what I got out from a coarse-grained Are they the same? Or
Oh, you mean compare the modes?
Yeah.
Yeah, you could do that.
That's what I would interpret that statement to be literally. What you're actually doing is simply trying to cluster similarly moving this little coupling.
Right. So, but that in essence, that's the same thing. So you're trying to place your coarse-grained sites in such a way that you could reproduce the motion of from each mode. So, for example, if you took the modes of water and you had, the 2 hydrogens going in, let's say, and you didn't know how many atoms were there, but you said, I want to place 3 sites here. What this algorithm or method would do is place 3 sites where they should be, 1 on oxygen, 1 on hydrogen, so that you could have 1 stationary and 2 coming in. I mean, that's how that would optimize that residual. Because otherwise, I mean, yeah, that's the optimal positioning.
To make my question like this, exactly the same?
I see.
Or is it that physically they end up optimizing?
I think mathematically the same, but I haven't. That's just my intuition. I haven't actually derived it to make sure that it is the same. Yeah. Any other questions? All right. So these are the methods, or in particular, EDCG is the method that we use to place coarse-grained sites, and the example of the N-bar protein that I just showed you. Basically, we're going to work through that in the tutorial on how exactly to do that. And you can play around with a number of coarse-grained sites to figure out what you think is best, or whatever looks best. And you can also calculate the residual and see how that works. All right, so, sure, okay, we got 5 minutes. All right, so now we'll move on to deriving some interaction parameters. And likely I'll just talk about the first 2 and ignore the second one just for time's sake. But the idea is now we have these coarse-grained sites, and we've placed them on our underlying atomistic data. What do we do with it? How do we simulate? We ultimately want to do a coarse-grained simulation, likely. So how do we derive the interaction parameters between these things? One approach that Greg mentioned is the inverse Boltzmann approach. And we don't actually use it often in the group, but it has, quite a few people use it out there in the literature, and it has underlying statistical mechanics to it that tell you that actually, if you just from the probability distribution of a conformation Q, statistical mechanics will tell you that's proportional to the Boltzmann factor of the energy of that conformation. From that, you can calculate the free energy, basically, of that interaction from an all-atom simulation based on just the inverse Boltzmann. So this is called inverse Boltzmann, basically. You just take the natural log of each side. And so then the next step is we assume that we can take the conformation Q and separate that into, for example, uncoupled bonds, angles, and dihedrals. And that allows us to take this probability of a conformation Q and decompose it in R, theta, and phi. If we can do that, so by the way, this assumption, which I'll talk about in a second, is not always valid. You cannot always decouple these into bonds, angles, and dihedrals. But if you can, then you can say that the interaction potential of a bond is equal to the natural log, basically, of the probability of that bond distance divided by a volume factor. And theta, again, is the same thing, and phi is the same thing. So you can define, like an all-atom simulation, a topology of your coarse-grained model and derive all of its interaction potentials just by looking at the probability of, in the case of a bond, just that bond distance from your all-atom trajectory. So that means a center of mass to center of mass distance. And then you can derive these interaction potentials. And so let me show you an example, which you won't do in the tutorial. But again, here's actin, which you've seen a few times at this point. And we have all-atom trajectory of an actin monomer. And we've mapped it into this 12-site, now I've only shown 11 here, but a 12-site model. And I look just particularly at one bond distance. So in this case, this is subdomain 1, and this is subdomain 2. And I look at just how that center of mass distance fluctuates throughout my trajectory. And if I just plot that probability density, you get this dotted dash line, this dashed line here. Okay? And then if you do what was called the Boltzmann inversion, you get this gray line, or the gray points here. And that is your interaction potential. Okay? So the free energy, basically, in kcals per mole on the left, and the probability density is on the units on the right of this plot. So from this data, for the Boltzmann inversion interaction, you can run, so this is one example, this is just a bond, right? So you have to do this for the entire topology of your system. Then you can take this and run in a tabulated form. So you just, as Greg said, you fit a spline or whatever to this and you feed it into your MD simulator or whatever in a tabulated form, and you run based on that free energy. You can also try to fit this thing. So I've shown here some fits to this data. So here's, I think this is a cubic versus this green line's a quartic, just polynomial. So you can try to fit to that and then feed that information in. But most modern day MD simulators will allow you to use tabulated potentials. So that tends to be the way we go. So as I mentioned, though, the decoupling assumption is not always valid. And what do I mean by that? Well, I did all of that. I derived all of those interaction potentials for this topology. So that means all of these bonds that are shown here, I got bonded potentials. And then for all of the angles and subsequent and dihedrals that result from that topology, I've also gotten those parameters from my atomistic simulation. That allows me to run a coarse-grain simulation of this thing depicted here, which is supposed to go, if it, let me click it. Okay, so this thing bounces around now. This is a coarse-grain simulation based on all of those interaction potentials. And then from this simulation, I can calculate the probability density, again, of this bond distance. And if everything were uncoupled and those interaction potentials I initially showed you were valid, you would get exactly the atomistic probability density back. But it turns out you don't. You get this purple line here. Okay, so that implies that there's some coupling between different bonds or different angles or different dihedrals. And so you can, what's called the iterative Boltzmann method, incorporate some of this coupling using iteration. And you take the initial, so your initial derived interaction potential, and you add some correcting energy. That correcting energy is just defined as the difference, basically, between the probability density that you get from your coarse-grain simulation to your atomistic one. And so that you have to do this a number of times till basically, I don't have a plot here, but basically this purple distribution will match exactly or closely your all-atom distribution. Okay, so just to recap on what so you can use this iterative or an inverse Boltzmann to determine all bonded parameters, but also non-bonded parameters too. It doesn't really differentiate between those two things. You have to differentiate between angles and dihedrals just based on whatever probability densities and stuff you're looking at. The downside of this is for the bonded potentials, as I mentioned, it requires you to define a topology for your coarse-grain model, which to me doesn't always make sense. I don't always know immediately what should be bonded to what and what shouldn't be bonded and what dihedrals I should be important. So this I think is a real downside to that, to the iterative Boltzmann method, and something that actually, funnily enough, hetero ENM or elastic network models avoid by just hetero elastic network models. All they do is just define bonds between each of your coarse-grain sites. So again, if you looked at Acton, you define 12 coarse-grain sites, and all pairs within that 12 coarse-grain site model would just have bonds between them, and no angles, no dihedrals, no nothing. And so then you just basically have a whole bunch of springs connecting everything together, and it sort of fluctuates like, elastic network. One thing, however, that the Voth group has improved upon for standard, or not just the Voth group, but multiple people. The standard elastic network model uses the same spring constant for all springs within a model like this, which is not always a great assumption. And so what hetero ENM, or heterogeneous elastic network model is it treats each spring differently, has a different force constant. And again, using some sort of iterative approach, tries to match it, the fluctuations of the coarse-grain model to the all-atom model. And so it initially approximates or estimates that force constant, K, and then for each pair, it iterates over this function. So basically trying to, in this case, this is your coarse-grain fluctuation projected onto your normal mode, matching that to your all-atom molecular dynamics data of that same pair. And so what do you get for actin? Well, unfortunately, plots for this are kind of hard to show, but here, again, I have that same picture of the actin monomer, and here now I have my coarse-grain beads connected by a whole bunch of springs, okay? But these springs have been color-coded to show you which are strong and which are weak, okay? And this is, I think, why the hetero-E&M model is, does some improvement on the iterative Boltzmann model in that you don't define a topology, but that topology sort of falls out because some of these springs, like for example, the spring between this bead and this bead, or this bead and this bead, are blue, okay? Blue, in this case, in this color coding, is a very weak spring. So that's telling you immediately that there's a very weak bonded interaction between those guys. Whereas if you look at, say, this bead to this bead, you get a red spring, and red spring is greater, it's something like 1 to 12 kcals per mole per angstrom squared. So that's telling you you have a strong spring connecting those things. Thus, there's strong correlation between the motion of those guys. And this type of approach can be, this is the strong bonds in an entire actin filament from an MD simulation again. And so this approach can be used easily on these large systems and then can mimic that sort of Gaussian type behavior of a large protein. Yeah?
Do you always use this sort of procedure to kind of some bonds, or you put
So in the standard E&M model, there is some cutoff distance from which you don't think of two particles to be bonded together. In the hetero E&M approach, you don't need that cutoff because that should fall out from this model. Basically, all these things are bonded together. However, some of them have almost negligible spring constants between them, thus are likely not, you can likely just chop that spring and not consider it.
Although something negligible will get really big when it's being squared, right? Okay.
Right, but you're
not unfolding these things.
No, yes, absolutely, no. So, well, we're running into the thing, so I won't talk about the field matching. But anyways, I have a downside of. I'm sorry. So, just pitfalls. Here we go. That's what it is. Not downsides, but pitfalls. So. Exactly what you just said right here. Hetero E&M does not allow for large conformational changes. So if you derive an elastic network or even a hetero E&M model for a protein, you're never going to see it do a large conformational change. You'll have to have two. So there are some models, actually Benoit's group has done some of this, where you have two hetero E&M models for different largely different conformations, and you can go between those based on some transition function or something like that. But similarly, the iterative Boltzmann procedure is also going to bias towards whatever you have derived those parameters based on. So I don't think that the iterative or inverse Boltzmann will improve upon that. And so I didn't talk about the electrostatic potential matching, but you can get those slides just like the one Greg skipped. We'll provide those for you. So with that, I mean, I'm just happy to take any questions. And we will talk about a lot of what I mentioned will be done in the tutorials either today or tomorrow. Yeah, you have a question?
Proteins that have do you think these methods would be better applied to proteins that have like a specifically defined structure? structure, a stable structure, whereas like the intrinsically disordered proteins. For
Sure.
example,
Yeah, you're never going, these methods that I've mentioned will not, unless you do something like the two-state E&M model, will never show you a folding procedure or something like that. So now, if you have an intrinsically disordered polymer that's never going to really fold up on itself, I think some of these methods could derive parameters for that, certainly. Yeah. Yeah, Benoit?
I have a question. If you have a coarse-grain model with a certain number of balls,
Mm-hmm.
and you do the elastic network model, find the strength of the spring between all these balls,
Mm-hmm.
you decide that a spring constant below a certain threshold is not worth the bother, and so you decide to erase those
Mm-hmm.
springs. Is the algorithm going to refresh the force constant for the other ones to compensate for the fact that you deleted some?
I actually don't think you.
It would, or
You think it would? Well, I've actually never run it, so June's the expert
it will
here.
change the,
You can determine which bonds you want to find or not. You can delete them and
Yeah, but what she's
the
asking,
question is like,
yeah.
in a kind of quasi-harmonic picture, they would be not renormalized, I suppose.
I think, yeah.
They would be,
Yeah.
okay.
Any other questions? Yeah.
In the cases where you discard the constant, you will make an interaction for the energens and kind of
So there actually have been some, you can talk to Anton. He's been trying to improve upon the harmonic approximation in this regard, but you would obviously have to, start from the beginning, fit to a different function, right? So basically then you'd be doing the iterative Boltzmann, more or less, right? Or actually an approximation on the iterative Boltzmann. Yeah.
Are there any advantages to defining your topology in a inverse Boltzmann approach compared to the hetero E&M mode?
Well, there are potentially, because you can, if you know, for example, in the actin situation, you have, with hetero E&M, you just have a bunch of springs, right? And so you'll never get these large conformational changes. However, in iterative Boltzmann, you'll never will either if you fit all of those interaction potentials to one particular simulation, because they would only reproduce that simulation. But however, if you intrinsically, or if you've determined something about one of those conformations, so for example, in the actin, one particular important thing is the rotation about, I'm not going to get to it, but there's some particular dihedral that's important that, for example, people have calculated, a larger PMF for, and then so you could think about fitting to that function as opposed to the function you're getting out of your one simulation. So that's at least my take on it. Okay. Well, there's coffee hour or coffee half 20 minutes. Yeah. So there's coffee outside, and we'll meet back here in 20 minutes for a session at 11.